In this video, we will prove the robustness to post-processing of differential privacy. Recall the setting. A differentially private mechanism inputs a private database and outputs some reply that supposedly depends on the private database. The mechanism is epsilon delta differentially private if for any two databases X and Y that differ on one entry only, the mechanism returns the same reply with high probability. More precisely, for any possible set of responses R, we have the probability that m of x is in R is at most e to the epsilon times the probability that m of y is in R plus delta. For more on this definition, I refer you to the previous videos I made. The robustness theorem asserts that no matter what the hacker does with the reply R, he will not be able to break the epsilon delta differential privacy. More precisely, this corresponds to saying that for any post-processing function f to the set of replies to the set of data, we have the probability that f of m of x is in a set D of data is at most e to the epsilon times the probability that f of m of y is in D plus delta. In other words, if m is epsilon delta differentially private, then so is the composition of f and m. And this actually holds even if f is a randomized function. Let's prove the theorem. We restrict ourselves to deterministic post-processing for today. The more general case is slightly more technical, but it's not much more difficult. The proof is very straightforward. We have the probability that f of m of x is in D is equal to the probability that m of x is in f minus 1 of D, that is the subset of responses R such that f of R belongs to D. And this is at most by differential privacy of m e to the epsilon times the probability that m of y is in f minus 1 of D plus delta, and this is equal to e to the epsilon times the probability that f of m of y is in D plus delta QED.